Hello dear students of medical, non-medical and respected teachers. In this video I am going to discuss simple harmonic motion and its characteristics. So first of all, what do you mean by simple harmonic motion? And to understand simple harmonic motion, first of all, what is periodic motion? So any motion which repeats itself again and again after regular intervals of time is called periodic motion. For example, rotation of earth about its axis, rotation of a planet around the sun, oscillations of simple pendulum, vibrations of tuning fork, oscillation of the liquid in the limbs of U-tube, and so on. There are so many periodic motions. But simple harmonic motion is a special case of periodic motion. It is a special case of periodic motion. That is, every periodic motion is not a simple harmonic motion, but every simple harmonic motion is a periodic motion. So simple harmonic motion is a to and fro motion about a certain fixed point called the mean position, and in case of simple harmonic motion, acceleration is directly proportional to its displacement from the mean position and it is directed toward the mean position. In other words, a particle or a body is said to be executing simple harmonic motion if its acceleration is directly proportional to its displacement from the mean position and it is directed towards the mean position. So, in case of S.H.M, A is directly proportional to minus y, or A can be written as d2y by dt2, second order differentiation of displacement, proportional to minus y, or d2y by dt2 is equal to minus omega square y, or d2y by dt2 plus omega square y is equal to 0, which is the required differential equation of simple harmonic motion. Any oscillating system or a body, if it obeys this equation or it satisfies this equation d2y by dt2 plus omega square y is equal to 0, oscillation of that body or system will be simple harmonic in nature. For example, oscillations of a simple pendulum are simple harmonic. Vibrations of tuning fork when it strikes with a rubber band are simple harmonic in nature. Vibrations or oscillations of liquid in the limbs of U-tube, so all are simple harmonic motion because S.H.M is a to and fro motion about a certain fixed point and acceleration is proportional to displacement and directed toward the mean position, so which is the required condition for simple harmonic motion. Now to study geometrical meaning of simple harmonic motion. Suppose a particle is moving in a circle of radius r with uniform speed, that is, it is a uniform circular motion. X O x dash and Y O y dash with the two perpendicular diameters, horizontal and vertical diameters of the circle. Now suppose when particle starts moving at t is equal to 0, it was at x. At t is equal to t, particle reaches at this point, which is at p. So this p is known as reference particle. Join OP is known as radius vector and OP is equal to r. From P, draw perpendicular PM on y dash. So then M is known as foot of the perpendicular or projection of P on the diameter of circle of reference. Let this angle XOP is equal to theta. Theta is equal to omega t by definition of angular frequency. So now then this particle P moves from X to Y on the circumference of circle, and we see that this particle m, that is foot of the perpendicular, or vibrating particle, also called vibrating particle, moves from O to Y. As P moves further from Y to X dash, this M moves from Y to O. As P moves from X dash to Y dash, M overshoots this origin called mean position and goes from O to Y dash. As P moves from Y dash to X again, that is, it completes one full rotation, M moves from Y dash to O again. So during the time, the reference particle P completes one rotation like this. This foot of the perpendicular, that is vibrating particle M, completes one vibration. This is called one vibration. And when second vibration starts, again this is repeated. It means reference particle goes on moving on circumference of a circle with uniform speed. This M goes on moving between two extreme positions Y and Y dash about O like this, and this to and fro motion is nothing but simple harmonic motion, because we will prove in this case A is directly proportional to minus Y. So if this condition is satisfied and is to and fro motion, then it should be simple harmonic motion. It means, what is M? M is the projection of P on the diameter of circle of reference. It means simple harmonic motion. Geometrically, simple harmonic motion is the projection of uniform circular motion on the diameter of circle of reference. This is the geometrical meaning of simple harmonic motion. Now, why it is called simple harmonic motion? Because it is very simple motion, not complicated to and fro motion from a certain fixed point, not complicated. Harmonic because its displacement, velocity, they can be expressed in harmonic functions. We will derive expression for displacement. So it is harmonic, it is periodic. So that's why it is called simple harmonic motion. For example, the name of harmonium is also given on the basis of this simple harmonic motion. So because of motion of harmonium is also to and fro, and it is harmonic, musical, periodic. So this is the geometrical meaning of simple harmonic motion. Now we come to characteristics of simple harmonic motion. First is displacement of particle executing simple harmonic motion like M. So displacement of particle executing simple harmonic motion is nothing but its distance from the mean position at that instant. So displacement of a particle executing simple harmonic motion at any instant is equal to its distance from the mean position at that instant, because this displacement goes on changing as particle is vibrating about its mean position. So that OM is equal to displacement is equal to y of the particle at t is equal to t. Then from this right angle triangle OMP we can find OM. So OM upon OP is equal to sin theta or sin omega t, or OM is y, OP is r, so y is equal to r sin omega t, which is required expression for instantaneous displacement of the particle executing simple harmonic motion. So y is equal to r sin omega t. So it is periodic. Sine wave is a periodic wave. Now at mean position, when particle M is at 0 O or P is at x or x dash, then y will be equal to 0 at mean position, and at extreme position y is equal to r. Distance between mean position and either extreme position is also called amplitude of the particle executing simple harmonic motion. So the maximum value of displacement of the particle executing executing simple harmonic motion is known as amplitude of the particle executing S.H.M. So y is equal to r is equal to maximum is called amplitude. Then it means the displacement of particle executing S.H.M is maximum at the extreme position, either extreme, and minimum at the mean position. Then we come to velocity. Velocity of particle is defined as the rate of change of displacement. So differentiating this equation, number 2 with respect to we have dy by dt, r dy by dt of sin omega t is cos omega t or into omega. So V is equal to R omega cos omega t. So to multiply with the coefficient of t. So dy dt of sin theta is cos theta. So V is equal to R omega cos omega t, which is the required expression for velocity of the particle executing S.H.M at any instant. Also, if we find the velocity of cos omega, value of cos omega t from this right angle triangle. So from right angle triangle OMP again, cos omega t is equal to MP over OP, because this angle theta, this is also theta. MP based upon hypotenuse, MP upon OP. Now MP using Pythagoras theorem can be written as OP square minus OM square root. So OP square minus OM square root upon OP. OP is R square, OM is Y square root upon R. Such the value of cos omega t in this equation number 3. So we have V is equal to R omega under root R square minus Y square upon R cancels, or V is equal to omega into under root R square minus Y square. So this equation gives the velocity of the particle executing simple harmonic motion when displacement is given, when displacement is y. This gives at any instant t. So both are the expressions for velocity at any time and when displacement is y. Now at mean position, we know that y is equal to 0 or t is equal to 0, cos 0 is equal to, at mean position, y is equal to 0 or t is equal to 0. So sin 0 0, y is equal to, so v is equal to r omega. From this cos omega t, cos 0 is 1, or from this put y is equal to 0, so it will be r omega. So at mean position, displacement of the particle executing S.H.M is 0, but velocity of the particle executing S.H.M is maximum, r omega. At extreme position, y is equal to r or t is equal to t by 4, 1/4 of time period. Then v is equal to 0, that is velocity is minimum, because cos 90 is 0. So therefore, velocity of a particle executing S.H.M is maximum at the mean position and minimum at the extreme position. Then acceleration defined as the rate of change of velocity. So a is equal to d by dt, or differentiating it, equation number 3. So we have a is equal to d by dt is equal to r omega d by dt of cos omega t is minus sin omega t, multiplied by omega, so it will be minus r omega square sin omega t, or r sin omega t is nothing but y. So a is equal to minus omega square y, or a is proportional to y, which is the required condition for simple harmonic motion that we have proved. That is, in case of simple harmonic motion, acceleration is directly proportional to displacement from the mean position and directed toward the mean position. And it is a to and fro motion. So a is proportional to minus y. So at mean position, y is 0, a is 0. At extreme position, y is equal to r, a is equal to r omega square numerically. So it means acceleration of a particle executing simple harmonic motion is minimum at the mean position and maximum at the extreme position. That's why it is directed toward the mean position. So when particle goes to either extreme, so it is back due to this acceleration which acts toward the mean position. Then time taken to complete one vibration or one oscillation is called time period. As a is equal to omega square y, from this we can find omega square y upon a, or omega is equal to y upon a, or omega is 2 pi by t, or t is equal to 2 pi under root y upon a, or is equal to 2 pi under root displacement upon acceleration. It is time period of a particle executing S.H.M is given by t is equal to 2 pi square root of displacement over acceleration. But displacement over acceleration ratio is constant from this equation, which is equal to omega square. It means, very important thing, time period of a particle executing simple harmonic motion is independent of its displacement or amplitude from the mean position. Amplitude from the mean position. Time period is independent of displacement, velocity, displacement or amplitude from the mean position. Then frequency, number of vibrations per second, number of rotations per second, number of oscillations per second, which is given by reciprocal of time period. Nu is equal to 1 upon t. Angular frequency defined as 2 pi by t, or 2 pi times the frequency. And last is phase. So what do we mean by phase of a particle executing simple harmonic motion? So phase of particle executing S.H.M gives a state of oscillation with both regards its position as well as direction. So by knowing phase, we can note the position of the particle as well as its direction. So suppose particle is again moving on circumference of circle, and particle is at x, starts moving and it covers phase angle pi by 2. That is when particle reaches y. So its phase will be either t by 4, 1/4 of time period, or pi by 2. So phase of particle is equal to fractional multiple of time period t or corresponding phase 2 pi. So at y it will be 1/4 of t or 1/4 of 2 pi, that is t by 4 or pi by 2. At x dash it will be 1/4 of x dash it will be half of t, that is t by 2 or half of 2 pi, that is pi. Similarly at y dash it will be 3t by 4, 3/4 of t or 3/4 of 2 pi, and at x again it will be t or 2 pi. So when reference particle completes one full vibration, its phase will be t, it means it reaches mean position. When particle is y, its phase is t by 4 or pi by 2, it means it is at y and directed toward the mean position. When its phase is t by 2 or pi, it means it is at x, that is correspond to x, corresponding is on the mean position. So by knowing phase angle, we can find the position as a direction of the particle executing simple harmonic motion. So this is 1/4 of t, 1/2, 3/4 and so on. So this is all about what is simple harmonic motion, what is its geometrical meaning, and what are the main characteristics of simple harmonic motion. And you have to remember all these equations. This is differential equation of S.H.M. Sometimes any y displacement is given, y is equal to r cos omega t, y is equal to a sin omega t plus b cos omega t. You are asked to prove that, show that it represents simple harmonic motion. Then you have to differentiate that equation twice, and if equation comes out of this form, then oscillations are simple harmonic motion, or that equation represents simple harmonic motion. So y is equal to r sin omega t, v is equal to r omega cos omega t, or v is equal to omega into root r square minus y square, a is equal to minus omega square y, t is equal to 2 pi into displacement of acceleration square root. So therefore you have to remember all these expressions to understand simple harmonic motion. Further, in the next video I will discuss oscillations of simple pendulum and a mass attached to a spring are simple harmonic in nature, and we will derive the expression for time period of simple pendulum. So till then, all the best, be happy, good luck, and stay tuned. Subscribe my channel. You will find all the videos on all topics of 9th to 10th, 11th, 12th class in the future. Good luck.